so let's now try to understand the the search in multiple scales, and this is actually quite interesting. We'll spend some time on this. So let's see how we can actually perform this automatic scale selection. Okay, so one brute force way will be, let's say you have this particular object which you're interested in, and you can see like this is much bigger scale, right? The object appears bigger as compared to this one, but of course this is the same object. Now it's easier for us to say that these are the same objects because we are kind of, our vision system is scale invariant. It's very powerful, right? We can easily take into account that, okay, this is a smaller object and this is a bigger object. And taking that into account, we can say that, okay, these are the same objects. But the computer vision algorithm doesn't know that these scales are actually different. And it will try to match these two without taking that scale into account, and which makes it very, very challenging. All right, so let's see how we can do that automatically in computer vision system as well. Now, if you look into this yellow bounding box here, so this is a very small bounding box, and this is, let's say, is one key point present in this image. Now, if we look at the same key point on the second image on the right, which has a bigger scale, of course, the bounding box will be much bigger. If we have to look into the same amount of pixels, which we're looking into the first image, right? Of course, the number of pixels will be different, but the actual visual content is actually similar when we take a much bigger bounding box. Okay. So now the goal is how we can figure this out that, okay, this box is, if the scale is 1x, this scale should be 3x. All right. So let's try to go over this. So what we do, we do like a brute force mechanism here, but again, try to understand how this can be done automatically. So we take like a bounding box. It's very small. We start with very small bounding box. And we don't care because we don't know what are the scales in these two images. Okay, we just assume, okay, they are different or they are same. We don't care. So we start with a very small bounding box of same size. And we, let's say, try to perform filtering at this location. All right, so this is, let's say, your kernel and some kernel, and you're trying to capture some kind of response. And let's say if the pattern of the kernel matches with the patch at that location, then you should get like a very high response, right? That you know from filtering. So we start with a very small bounding box, and we try to capture the response. And what we do, let's say we start with this. So on the on the x-axis, we have the scale, which is kind of giving you the size of the bounding box. And on the y-axis, we have the response from the filtering operation, whether the filter is actually matching with the image patch or not. And that's the white dot over here. And you can see that when we start with this scale on the left image, then we are getting somewhat like a higher response. But in this case, we are getting a smaller response, which could be because this size filter is actually matching very well with this location, but not with this location. And we know the reason because this has a bigger scale, right? It will, of course, not match. Now, what we can do is we can keep increasing the size of this bounding box. And here you can see that, okay, the response is actually improving further, which means the kernel is actually even matching better. And even in this case, the response is actually increasing. Okay, so as we go right, here you can see that, okay, maybe this scale over here, so this is 3.8, right? So some random scale. And this tells you when your kernel size or your bounding box size is 3.8, then whatever kernel you're using, it's actually matching perfectly with that image patch. And that is giving you the highest response. All right, so which means that to be able to detect this particular pattern in your input image, this is the right scale. Okay, 3.8, and that scale is specific to this image. And you can see that as you keep increasing the bounding box, the response is going down because the actual pattern which you're looking for, it will no longer match, right? The visual features are actually changing. And if you look at the second one, you can see that again, you saw like a peak, but at a much higher scale, which means that for this image, this scale, I don't know what this number is. It's actually hidden behind the transcript. So this is, let's say, 10, right? So a scale of 10 actually matches perfectly with this particular image. Now, why this is interesting? Because you're not changing the filter, you are just changing the size of the image patch on which you're applying the filter. And if in these two images, the same filter is actually giving you similar kind of response, or you can say high response at two different scales, then that in a way is telling you what is the scale difference between these two images. Okay, which means that 3.8 like kind of bounding box is equivalent to 10 times of bounding box when placed on this image. So that's giving you the ratio of the scale you have between these two images. So of course you can automate this process, right? Once you know that, of course we'll have to aberrate across like multiple scales. And that's the idea which is used when we extract SIFT features. What we try to do is we try to apply these kernels or filters at multiple scales. Okay, so that brings in like the idea of scale invariance into the SIFT features. And visually as a human, you can see that, okay, whatever visual information you have inside this box actually matches perfectly with whatever information you have in this bigger box.